Hey YouTube, what's up? Today we're going to solve problem number 62 from Leetcode, unique paths. Let's read the question first before we move on to the solution of the question. A robot is located at the top left corner of m times n grid, marked start in the diagram below. The robot can only move either down or right at any point in time. The robot is trying to reach the bottom right corner of the grid, marked finish in the diagram below. How many possible unique paths are there? Let me try to make the question clear. Our grid could be of any size, that's m times n, but our robot always starts from the top left corner, right? This is where our robot will be located. And then our objective is to reach till the end. So end is bottom right corner, right? But there is two conditions. Our robot can either move to the cell to the right of it or towards the cell below it, one step, right? It can't go to the left or it can't go to the up. Let's see how robot can move. It can move here, and then from this point it can either go down, right, or it can either go to the right, right? From this point as well it can go down or it can go to the right as well, right? So what the question is asking is, how many possible ways are there to reach to this point? So one possible way could be our robot could go all the way to the top right, and then from here it could go down all the way to the bottom right, and this is one way. Our robot could go all the way to till this cell, and from here it could go down here, and then from here it could take right. So this is second possible path, right? But instead of going down from this cell, it could also go here, and then from here it could go down. So this is another path. So this is third path for the robot. It could also go from here all the way here, and then from here it could go all the way to this point. So these are some of the pathways. The question is asking how many possible pathways are there. So we're going to solve this problem using two techniques. The first one would be recursion, and then the second one would be dynamic programming. Among these two, dynamic programming would be much faster, although it takes a little more memory, I guess. We'll have to see. And in terms of code, the recursion would be much shorter, but then it'd be hard to visualize as well, because we're going to call the same function couple of times, not even one. So what we're going to do is, in the recursion, the first technique, we're going to pass this coordinate to our function, right? So this one is 0, 0. Our last cell would be, according to question, m times n. Since we are starting from 0, 0, the actual value of the cell or address of the cell would be m minus 1 and n minus 1. So what we're going to do is, every time our robot moves, doesn't matter whether it's going to the right or it's going to the cell below it, we're going to check if the current cell address is m minus 1 and n minus 1 or not. If it is, we're going to create some variable, maybe a counter or something, and then when the condition satisfies, when the current cell address is m minus 1 and n minus 1, then we're going to add 1 to the counter. So that's how this algorithm is going to work. Let's write it. Let's create two variables, m and n, and it's going to take this as input. This will be our row and column of the grid, and we're going to output the unique path. Let's call it this recursion, because we're also going to write another function using dp, and then we're going to pass these two. So we need integer return type, because we want to return the total number of unique paths. So usually when I do recursion, I create a function called util, because we also need extra parameters, current location of our robot. M and n would be the size of the grid, and x and y would be the current location of the robot. I think it'll be more clear once I call that function from this point. Recursion util, I'm going to call that function from here. We'll just pass m and n as it is, and then we're going to pass the x and y would be 0 and 0, right? Because our robot always starts from the top left corner of the grid. And over here what we're going to do is, we're going to call the function itself, recursion util. M and n is not going to change because the size of the grid is always same. And then first we're going to move to the right, okay? We could decide to do anything, like we could go down first as well, or we could go to the right as well. Let's just decide that we'll go right first. So right would be the change in column, and then down would be the change in row. I'm going to keep x as it is and then add 1 to the y. I'm going to copy this, paste it again, and this time what I'm going to do is I'm going to add 1 to the row. So that means the above function, this one will take our robot 1 to the right to the next column, and then this one would take our robot to the cell below it. But if you just leave it like this is never going to end. It'll keep on going, right? So we need some breaking condition. So what's the breaking condition? Let's analyze this thing first. So breaking condition would be we wouldn't want to exceed the grid size. If the location of the robot tries to exceed this point, then we will have to return. And even at this point, if the location of the robot tries to exceed this point, we'll have to return. And what's this point? This point is n-1, and then this point is m-1. Let's go back, and then I'm going to write return condition. If x is greater than equal to m-1 or y is greater than equal to n-1, then we're going to return 0. If x equals m-1 and y equals n-1, then we're going to return 1. You remember we just talked about this cell. So if the current location of the robot is this, then we have found one pathway. So what we're going to do here is we're going to return 1. But now what happens is we want to count how many ones we returned. For that, let's create two variables. Right direction would be this, and then this one would be down direction. So what we want to return? We would want to return right direction plus down direction. So this would be our solution. Let's run the program and then see if this works. Okay, unique path was not declared in line 12. Let's go to line 12. Okay, so there is a typo in here. Right, so what did we get? We got 0. So there is something is not working here. Let's see. Okay, so this one should be greater than equal to 1, greater than equal to 1. Okay, so we have 28. So the thing was, we checked if x is equal to m-1 and y is equal to n-1, return 1. But then just above that, we also said that if it's greater than equal to m-1 and y greater than equal to n-1, which is pretty much this, if this condition satisfied, then this condition, the condition in line number 5 would have been satisfied already, right? So we're always returning 0. So we have 28 here. So this is way 1. What we're doing is we're creating this function, unique path recursion util. What it's doing is it's calling the function itself unique path recursion util m and x and y plus 1. So when we do y plus 1, what happens is this function will call itself. So it's going to call itself. Next time we're going to go to the next cell, and then the function would again call itself. This function would call itself, and then when it goes down here, this would again call itself. So before we move on to the line 8, right, the line 7 would keep calling the function until and unless we reach this point, because we haven't found out the breaking condition until now. And from this point, when it tries to go to the right, this is the breaking condition. So if we check our code, if x is greater than equal to m or y is greater than equal to n, then return 0. This is the first time we have returned from the function, right? From this point, if you notice, we have already called 2, 3, 4, 5, 6, 7 times. We have called that function 7 times. When we're at this point, we'll have to return 7 times to finally come out of this loop and then go to this function. So when we come out of the last function, we're going to go one step down for the last function, not this one, not down from here, but down from here, because when we return from this point, we are at this cell, and then from this point again, when you go to this point, this is going to call the function itself. Again, it's trying to go to the right. Even from this point, it will try to go to the right, but since there is no way, function will just return 0 and it will go down, and finally we reach the path. And then at this point, we're going to return 1, and that 1 will be returned to the function that was calling it, this function, and then this function would return it to this function would return this function, and then from this point we're going to go down. So that way, that 1 that we've returned would just compile up, accumulate in the return, and then until and unless we reach this point and we get the answer. So this is how the recursion function works. Now we're going to do the same problem using dynamic programming. So what we're going to do is, so our robot is at this point. We'll create a grid that's m times n size, and it will be of type integer. We're going to store 1 on all the first row and then 1 on all the first column. Why? Because when our robot goes from this point to this point, there are no other ways to reach to this point, right? There's only one way. Like if you go down, you can't go up, which means this row, for this row there's only one way to reach. Same thing for the row as well. For this row there's only one way. If you go to the right, there's no way you could come here, because at some point if you go to the right, to come to this point you will have to come to the left, and that step is not allowed. Your robot is not allowed to come to the left or to go up. We know that first row and first column, there's only one way to reach this point. Things become interesting from second column. At this point, so how many ways are there to reach to this point? What we're going to do is we're going to check the cell to the left of it, and then we're going to check the cell that's above it. There's one way we can reach to this cell, and there's one way we can reach to this cell. That means this cell is just the addition of these two cells. So there are two ways to reach these cells, because you can come from this point to this point. You can go to the right and then come down here. You can also go down and then come this side. I'm just going to erase this and make things a little clear. So there are two ways, from here and from here, two ways. What about this one? Now we know that to reach to this point, there are two ways. You can go one step right and then one step down, or you can go one step down and one step right. So that's two. To reach till this point, it's 2 plus 1, 3. Why? Because till this point, you know that you can take two pathways, and to come to this point as well, you can take two pathways from this side, right? Because you can come from this point, and here. You can also come from this point, and here. And then there's also another option from this side. You can go here and then come down. So basically what we're doing is we just see the cell to the left of it and then the cell above it, and then add two of those, and then we get the answer 3. How about this one? 4. This means that if our question was how many ways are there to reach to this point, then our answer would be 4. So what we're going to do is we're going to fill all the cell until and unless we reach this point. So this would be 5. It's pretty easy, right? 6. This is 3, and this is going to be 6. This is going to be 10. This is going to be 15. How is this 15? Because 10 plus 5 would be 15. The 10 ways to reach here and 5 ways to reach here. So these two would be 21. And this one would be 28. If you remember the answer, we got it from the recursion function, that was 28. So now how would you implement this in programming? Let's do that. So I'm going to call again the same function, the out, unique path, and this time it will be dp. I'm going to pass same thing, and I'm going to end the line. Here, what I'm going to do is recall the same function. So like we said, what I'm going to do is we need to create a placeholder for all these values, right? 1, 2, 3, 4, everything. So what should be the size? It should be m times n. So let's create a vector. We're going to create a 2D vector where, let's say dp. That's what people usually use for dp, and this is going to be m and n. I don't think we need to initialize this. If we have to, we'll come back later. But now what we need to do is like we said, the first row has to be 1, and then the first column has to be 1. So we're going to do that. I equals 0, I less than m plus I. So m is row. We're just going to do it in the same line. Here what I'm going to do is dp. So this is row, and then column is always 0. I'm going to assign 1 to this, and then same here. So n is the number of columns. This time we're going to set the row to be 0, and then this one would be I, and this is 1, right? So now this two line would make 1 on this side and then 1 on this side. Now we'll have to calculate all of these, like these numbers, and our answer would be the value in the last cell. So it's pretty easy now. So we would start from 1 because the first row and first column is already done. We would go to the last row. We'd also start from second column of the second row. This would be j plus j, and the logic here is now dp of I and j would be dp I minus 1, right? So this is, so we're going 1, we're taking the value from the row above it, and then plus we leave row as it is, and then we'll take the value from the column to the left. That is it. This is it. Now we would just have to return. What would we return? We would return m minus 1 and minus 1, right? Let's see if we get the answer using this. Throw here 3 and 7. Both of this gives us 28, right? So now before we end this video, let's try to see how many loops we have actually traversed in both of these functions. So I'm just going to create, I'm not a big fan of creating global variables, but for the purpose of just trying to understand how many times we've run, which one is heavy on computation, where we're going to create two global variables. We're going to call int recursion loop. It's not a loop actually, but then we're just going to call it loop for now. and then we're going to call this one DP loop just to make things easy so that we don't get confused later on. So here I'm going to write recursion loop plus plus. We're going to count how many times we have run this function, right, with this recursion loop, although the name might be deceiving. And then here we're going to do DP loop plus plus. Now what I'm going to do is, below the unique path recursion, I'm going to write down recursion loop indel, and then below this I'm going to do DP loop and indel, right? Let's run this and then throw in 3 and 7. See this, with the recursion thing, we call the recursion function 91 times, and for DP we called it only 12 times, and this is only 3 by 7 grid. Now if you think in thousands, then this number would drastically change. The conclusion here is there might be some other ways as well to solve this problem, but among these two, how would you decide which one you want to go for? Definitely the DP, right? But then for machines who has like infinite speed, like but very limited memory, you would want to go for recursion, but I'm not sure if that kind of device exists, right? Everybody is only searching for the faster algorithms, and then the memory thing is not a big issue for now, right? So I would say that DP is better way to do things, but then just to understand how recursion works, these are two ways to solve the problem. Thank you so much guys for watching the video. I hope you learned something from this video. I'll see you guys in another video, and please don't forget to like and subscribe to my channel, and until and unless we meet next time, take care of yourself. Bye bye.